All right, the big Scotsman is back. Dr. Morrison, to talk to us about the reperfusion injury. What's the danger, Johnny?
Good question. Death. Right, done. Thanks for having me back. It's final talk from myself, so after that you can relax. I'm now on first name terms with the AV guy. I'm waiting for an invite for beers with him. The title that I was asked to talk about was mitigation of reperfusion strategies, or the reperfusion injury mitigation strategies. Originally, a physiologist was going to give this talk, who's an expert in molecular bits and pieces, which I'm not. So I've done the great speaker thing of slightly changing how we do things and looking more at the kind of larger issues that we have. So what's the problem thinking about REBOA and reperfusion? Well, the problem is, as we've seen from these slides that I've shown earlier, is that for every increase in ischemic time, you've got a measurable outcome in terms of inflammatory response, a pro-inflammatory response, and that is harmful. And certainly we know that in some patients, they can have an exaggerated response, as we sometimes see in sepsis, and the same thing goes for systemic inflammatory response syndrome that we see in trauma. And it all really comes down to the tolerance to hemorrhage and ischemia. And with this figure, what I'm trying to illustrate is how that changes and where some of our clinical strategies are focused. On the x-axis, I've got our physiology and metabolic instability, which I've not yet assigned a parameter to measure that. You could measure interleukin-6, you could measure lactate, whatever your choice is, and then time. And clinically, what we have is every person comes in with some level of predetermined tolerance to injury, and that changes throughout life. Older patients have less robust physiology to injury and hypovolemia. Younger patients, slightly more robust. That wasn't me. Yeah, oh well. And importantly, that threshold changes, as I say, depending on age and genetics. And when faced with an injury, patients who are survivors are patients that have a response where they never peak above their tolerance to injury. And those patients who don't survive are those that exceed their tolerance to injury. This is the very unsophisticated surgical view of tolerance to hemorrhage and ischemia. And really, we've got two strategies clinically where we can either think about trying to move a patient below their tolerance to injury, or we can think about improving their tolerance to injury. And really what we've talked about recently have been some near-term goals, to my mind, in terms of partial occlusion, where, to my mind, partial occlusion is about limiting that further ischemic burden, where actually what you're trying to do is move your patient who features above that tolerance to injury, moving them down below that curve. And one thing that we haven't really touched upon has been actually increasing their tolerance to injury by modulating their cellular consequences to injury. Reducing ischemic burden isn't something that's unique to trauma. In fact, this is something that's been pursued in other lines, but in the context of REBOA, we've heard from our colleagues from Travis about their fascinating work with partial REBOA. And then there is the world of composite balloons, which may make elements of that easier. But as I was saying, improving the resilience to reperfusion injury is not something that is unique to trauma, and it's been explored in many other clinical arenas. This is a very famous paper from 1986, which was an experiment carried out in dogs by cardiologists who looked at two groups of patients. One group of animals where they had repeated interruptions to coronary flow by dissecting out and occluding the circumflex artery, and then a control group that didn't have interruption to flow. And when they then finally occluded that vessel in order to initiate a myocardial infarction, what was clear that those animals that had been preconditioned, that had had repeated areas of interruption to flow, in terms of the outcomes that they measured, it was very clear that those patients had a reduced size of infarct. So there was something that could be done to those patients that initiated or induced various proteins that resulted in a reduction in their injury. And that's where really the notion of ischemic preconditioning has come from, and how the tissue response to ischemia can be modified. And I think that that's something that we haven't really touched upon in a great deal today, but hopefully this might give some insight as to how this might look. So picking up where Jim left off, One of the things that we've talked about is passive aortic occlusion, or REBOA, which in this context I'm going to call passive aortic occlusion, where you've got an injury that's fed from a vascular region below where you've put your balloon in. In the context of the loss of spontaneous circulation, you can convert a passive aortic occlusion system like REBOA to an active aortic occlusion system like SAP, where you're able to deliver an intervention such as oxygenated blood through something like a cardio help. But then you can progress that even further to extracorporeal life support, where you put in a venous return limb, and then you're in a position to deliver perfusion above and below the balloon. This is purely an idea at this stage, although we've heard from Dr. Manning as to how some of that's been carried out in the laboratory. And what I guess I'm building at with this presentation is, can one infuse your magic fluid X? And when I came to talk about the notion of molecular mechanisms, well, there's a whole variety of things out there that one might be able to consider. This is hydrogen sulfide. This is a couple of figures from some experiments from a group that have used this in mice. And what's very clear is the infusion of this particular molecule results in a reduction in metabolic turnover. It results in a suspended animation-like stage. And I guess what I'm getting at is, in order to improve your ischemic threshold, devices or substances like this may well move that something that is within reach. In terms of things that are closer to home, well, the whole world of ischemia reperfusion injury is not something, fortunately, that I can have a stab at in 7 minutes comprehensively, but certainly there are substances out there that are being examined currently, such as statins. Tranexamic acid is known to have an anti-inflammatory effect. Melatonin, there's a trial ongoing in relation to melatonin. Erythropoietin, and then there's the long-standing University of Wisconsin solution used in transplant. So I guess before I take some questions, I guess in summary, I think that one thing that we've talked a lot about is trying to reduce the ischemic burden that patients are exposed to with interventions like REBOA. I think an alternative strategy is trying to look at something that will improve people's ischemic tolerance. And I think the notion of extracorporeal life support that Dr. Manning alluded to my mind, is that vehicle. So thank you very much. I'd be keen to take any questions.
Thank you, Johnny. I'll open it to the panel.
Anyone here? I've got a question for you, Johnny. So what's the future? Are we looking to give a fluid to mitigate? I mean, short of decreasing the burden that we're going to place on the patients, are we looking to infuse something? Should we cool these patients down? Are we going to dialyze something out of them? What's the way forward as far as our research goals? What should we be pursuing?
So, I mean, that's exactly the issue that we're trying to deal with. And certainly there are some preliminary works underway. There's the EPERCAT trial that's been led by Dr. Tischerman, I think I pronounced that right, which I think has recruited one patient. Their protocol is to essentially flush your vascular tree with a large volume of very cold saline. So they're really relying on hypothermia as being their mechanism of cellular protection. I think that that's absolutely a great start, and it's safe in that we know that deep hypothermic circulatory arrest has great utility, certainly in the cardiac world. But I think that we can be smarter than that. I think that that's a very broad brush approach to this sort of thing. I think that there are metabolic consequences of just using saline, and I think certainly tapping into some of these smarter agents, I think that sort of approach combined with a specific targeted approach to the molecular mechanisms, I think is the way forward.
And I think we have a question from the front row.
Thanks for reminding us of those interesting coronary studies with the intermittent balloon occlusion. As vascular surgeons, we are now fascinated by the perspective of perhaps inhibiting spinal cord ischemia by embolizing the intercostals.
Yep.
And there the effect is being suggested to be thanks to creation of collaterals. Could it actually be that by embolizing them, you also reprogram the metabolism of the, just like you suggested, could there be an interface between the two?
Well, I think undoubtedly, and I think, we've all seen, well, as vascular surgeons, we've all seen, angiograms of SFA occlusions where, one side you've had an acute on chronic event, on the other side you've still got chronic ischemia, where you've got, your SFA occlusion, and you've got, this great big leash of collateral vessels. We know that we see changes in the macrovasculature, but we also see, changes on a cellular level. you have the induction of NF-kappa B, various other proteins that are involved in improved resilience. So yeah, absolutely, I think there's multiple mechanisms at play.
One more brief question from the front.
Thank you for the presentation. One problem is that hundreds of substances has proven to be effective against reperfusion injury in experimental models, but none that I know has reached clinical practice. So that's a problem.
Yep, and I'm afraid I don't have an answer to that, but absolutely, you get into the meat of the biochemistry, and it's complicated, but translating that clinically, different ballgame. Thank you.
Thank you, Johnny.